Thanks for having me. It's fun to watch kind of your intro video. Very exciting to get to be involved in this. What I want to talk about today is a couple things that we've been doing with SPARTAN Robotics 971. It's a robotics team out of Mountain View High School. This is work done obviously with a much bigger group. I've called out a few names there of some of the key folks that have worked on the vision side of things, but obviously SPARTAN Robotics is a much bigger team that has been in this for a number of years, doing FRC robotics. What I want to talk about today is around our vision system. In particular, two things, and I'm going to go through them fairly quickly, but I'll try and cover both of them. One is how we do camera calibration, and the second piece is how we localize the robot on the field. And we've taken a new path this past season, where instead of using the reflective tapes, we're actually extracting features from the field and from kind of just the natural scenery on the field and localizing with respect to that. And so I'll talk about how we've gone about doing that. And feel free to interject, ask questions. I'm happy to. I'd love it to be interactive. Obviously, it's a little bit hard in this format, but yeah. Don't hesitate to ask if there's anything that's not clear, or I can expand on anything. All right, so let's dive into it. First off, what is camera? So first off, an outline of what I'm going to talk about. I'm going to start with just talking about what camera calibration means, like what I'm talking about by that term. Give a little bit of background on why that's important. I'll talk about how we do our intrinsic camera calibration in particular, and then spend probably the last half to third of this description on visual localization. So how we're solving the localization problem. Where's the robot on the field? All right, so first let's start with camera calibration, and what that is and what it looks like. The camera calibration really has two aspects to it. And let me just check. It looks like my video froze. Are you guys able to hear me still? Okay, so let me keep going. Intrinsic calibration, camera calibration has two aspects. One is what we call intrinsic calibration. This is just characterizing the camera itself. So what things like where is the image sensor relative to the lens? What's the focal length? How much zoom is there in the lens? Kind of lens distortions. And I'll describe that in a lot more detail. And then extrinsic calibration, which in contrast to kind of the internals of the camera, is about where the camera is located with respect to some reference frame. So where's the camera located with respect to the robot or other cameras, that type of thing. And I tried to link in a few references along the way. So in particular, I'm a huge fan of OpenCV, and so a lot of the links are towards that, and I highly recommend anyone who's wanting to get into vision to look at that package. It's just a great set of libraries for doing computer vision. But you can see within the camera calibration, in doing camera calibration, the goal is to really get accurate estimates of where things are in the world. So on the intrinsic calibration side, if you've got kind of a cheap lens or a poorly built camera, it introduces a number of distortions of where you think things are relative to where they actually are. And it can really drive significant errors in your estimates of where things are in the world. And in particular, the intrinsic calibration is really important when you're doing stereo depth, which we're not doing here, but just as a pointer to that. And similarly, extrinsic calibration is really important for stereo also. If you think about being able to use two cameras, you need to know where those cameras are with respect to each other. And that's really critical. And the other part of it is, if you want to know where an object in the world is relative to the robot, you need to know where that camera is relative to the robot. If you don't have that, or if that's wrong, it can really drive errors, and especially rotational errors can really be significant in how they compound themselves, because a small rotation can lead to large shifts in where you think something is in the world. If you're trying to track a ball, for example, and your heading is off, it really can drive large errors in your estimate. And I'll talk a little bit about what we do if we can't have like an automated calibration procedure. The typical approach is to use what I'll call CAD values. You measure with a tape measure where things are, or use your CAD model to figure out where things are relative to each other. For example, where the camera is relative to some reference frame on your robot. And similarly, there's things you can do with intrinsic camera calibration to use just kind of the default values that if you can't measure them directly. All right, so let's talk about real quickly what extrinsic calibration is, and this will be the last slide to talk about extrinsic calibration. I'll just reference that it's something we're working on right now, is to automate the extrinsic calibration procedure, but we haven't done that fully. So we've been using, like I said, just the kind of CAD values for where the cameras are with respect to the robot. But the idea with extrinsic calibration, it's a map from some coordinate frame, say the robot reference frame, I'll call that O, and a map of position and orientation, so a rotation and a translation that maps to the camera itself. And it's a idealized camera center, the frame attached to the camera, and I'll talk a lot about the camera frame. And what that map lets you to do is take points that are in the world, I'll call this P, so that I can let's say I can figure out where that point is relative to the camera. This map allows you to figure out where that point is relative to the robot. And so that's why extrinsic calibration is important. And again, a reference to just some the figure where this came from, that's got some good descriptions there. But let me switch over to intrinsic calibration. So intrinsic calibration is the thing that I'm just going to go through in detail and talk about. It's something we built up this year and have been finding it really, really important to get good estimates of where things are in the world. Without it, we found significant errors in our estimates. So intrinsic calibration, the first step is talking about what a camera, how does the camera work? What's the model for a camera? And we use, it's a simplified model, but it's a pretty robust one, is a perspective projection model, which means basically that objects in the world, and for example, I've written kind of like a few frames here, but objects in the world show up in the camera frame by projecting the ray that goes from the camera center, from the object to the camera center through an image plane. And it's kind of a conceptual image plane, but the point will show up in the image at that point. So talking about that a little bit more, let's say we have a camera frame, and typical notation in computer vision is the camera frame looks like this. It's got Z pointing out into the world, and then the X is kind of your row direction, call it horizontal direction maybe, in the camera sensor, and Y is a vertical direction but going down. So this is a typical camera frame. And if I'm given some point in the world P, the point in which that object or point is going to show up in the image frame is found by drawing the ray or drawing the line between the point and the camera's origin, and passing it through some projective plane that's at a distance that I'll talk about, but is the focal length from the camera, and then figuring out where it intersects. So it's a projection down to this kind of virtual plane, this camera image plane. And when we talk about it, there'll be some points in the world, X, Y, Z, that project down to 2 dimensions, because that's what an image looks like. And usually we'll use U and V to reference the image coordinates of the camera in the image. And as I was mentioning, the camera coordinates are always a little bit funny, that U is kind of this, is telling you what your column is actually. So it's kind of the horizontal reference, and V is the vertical coordinate. And a few other things that I'll talk about, that are important for camera calibration. One is called the principal point, and that's where the center of the image is. And what's interesting is in pretty much all cameras that we work with, the center of the image isn't actually, the principal point, the camera center, where this thing projects down to the middle of the image, isn't actually in the center of the image. And so that's really important. It's basically saying that that when I project something, even though I think maybe the thing straight in front of the camera should be in the center of the image, it actually isn't. And that's because very often when cameras are built, the sensors are plopped down on a circuit board, and the lens is plopped down on top of it. but the center of the lens and the center of the sensor aren't completely aligned, aren't perfectly aligned. And so that offset is what leads to the principal point of the camera not being the center of the image. And then the second thing that I'll talk about in fair detail is the focal length. So, and that's the distance from the kind of virtual camera center to this focal plane. So it's the Z distance, if you will, and I'll call that F. And that's really important, and you'll see lots of references when you look at cameras to focal length, often measured in millimeters. I'll talk a little bit about that. But this is also where you start to see things like zoom. You know, a very large focal length typically is a large zoom lens. So you get like a 100 millimeter lens. That means it's really heavily zoomed. So you're getting kind of your projection is very small because you're focusing on a small image. And in contrast, a wide angle, like a fisheye lens, will have a very short focal length because it's kind of the projective plane is very close to the lens, and so you're seeing a lot more. And perspective projection model basically just maps these X, Y, Z coordinates in the world into the image coordinates. Okay, so that was a lot. Let me take one more look at it just to make sure we're kind of talking about the same thing. But when I think of perspective projections, I tend to think about similar triangles. So using similar triangles. In this case, let's just pretend that I've taken a slice that is along the center horizontally of the image, and now I'm just looking at just a slice in the vertical part of the image. And so if my camera center is here and my focal length is this thing F, which is just the kind of halfway across, then if I've got my world point P that has some location X, Y, and Z, again, I'm kind of dropping X just in the simple model, then the point is at some depth Z from the camera and some height Y above kind of the camera axis. And then if I want to think about what this projection is doing, again, what I'm trying to do is take some world point X, Y, Z and project it to some image point UV. In this very simple kind of slice, I can think of that as taking just the Y coordinate, Y coordinate of the point relative to the Z coordinate of the point. That's one triangle, kind of a large triangle. And comparing that to the smaller triangle, which has a vertical of V, which is the image point, and the focal length F. So put that together, the ratio between Y and Z of the large triangle is going to be equal to the ratio between V and F by similar triangles. Or stated another way, our V, the height in the image plane, in the image, is going to be equal to the focal length times the ratio between Y and Z. So I'm essentially normalizing by the depth. So that's going to be how I project, is normalized by the depth and scale by the focal length. And similarly, if I want to do that in the horizontal direction, it's U equals F times X over Z. So same thing. Okay, so that's kind of the simplified model of how I think about projection. As we get one level more complicated, there's a couple more adjustments we have to make just to make this more accurate and correct. So two adjustments to make in particular around this projection. So it's unfortunately not quite as simple as V equals Y times F over Z, because we actually have to shift around the principal point. Remember that the origin for the image, where this thing projects, the origin in the image plane is the top left corner, but the center where this thing projects around is in the center roughly of the image around the principal point. So we're going to have to shift V and U by this center point. So it's going to be based on the principal point, CX, and we'll call it CX and CY. So CX and CY just measure in pixels where the center, where the principal point is in the image. And then the second piece is that focal length, I mentioned, is often measured in millimeters, but it's actually in practice very often measured in pixels. And in order to have this equation make sense, this V equals Y times F over Z, it needs to be in pixels because V is in pixels y divided by z is going to be a non-dimensional or unitless parameter or quantity, and f has got to be in pixels. So we need to translate a focal length that typically is measured in millimeters or in some metric unit into pixels. And when we do that, because pixels aren't always square, we get a separate focal length in the x and y direction, because the number and size of a pixel might be different in the x and y direction. So we'll end up with two focal lengths, one for the focal length in x, and one focal length in y, both measured in pixels. Okay, so that's a lot of setup, but what that leads to is an intrinsic calibration that looks like this, where our horizontal projection looks like the focal length in the x direction times this projected value of the x distance divided by the depth of the point plus some center offset. So it's the shift by the principal point, and the same thing for v. And so intrinsic calibration, and this is what we're building up to, intrinsic calibration is about estimating those quantities. Okay, so taking a given camera and estimating what they are. And just when we thought we're almost there, there's one more thing to talk about intrinsic camera calibration, and that's lens distortion. And that's a different component. It's different than just your projective coordinates, but it's what happens when you have lenses that don't perfectly project down into a plane. There can be some distortion, and this happens in real life with lenses, and especially if the cheaper the lens and the smaller the lens, the more likely you have distortion there. So this is a quantity that we also measure and take into account when we do intrinsic calibration. And I've got references in here to the OpenCV toolbox that really allows you to understand that. I'll really quickly talk about lens distortion. I don't want to focus on it, but I would be wrong not to mention it. So the distortion for lenses, I've kind of shown a few types of distortion. There's the very typical approach is to look at just purely radial distortion, where the amount of distortion or shift is proportional to how far you are from the center. So that leads to two basic types of distortion, actually. So you have no distortion, that's the perfect case. A positive radial distortion is what's called sometimes a barrel distortion. It looks almost like a barrel shape. And a negative radial distortion is sometimes referred to as a pincushion distortion. It's almost like you pushed a pin into a cushion, and so it's kind of folding in that way. And these are the types of distortion you might expect to see. You've probably seen images like this. The radial distortion positive radial distortion, barrel distortion very often happens when you've got like a fisheye lens, very wide angle lens, that you're trying to capture a lot of information and gets distorted out on the edges. The pincushion distortion is maybe a little less common, but happens more typically with zoom lenses. So you're trying to zoom out and you get some of this pincushion distortion. Okay. And again, I'm not going to try and dive into this one. It gets a little bit complex, but here's kind of equations for the lens distortion models. And so intrinsic camera calibration also involves estimating these parameters. It looks pretty complex, and it is kind of, but again, the calibration procedures typically will account for these. But you'll get some corrective factors. So if you do your projection, kind of this is the simple view of the projection, the projection corrected for the distortion has these kind of quadratic terms in it, based on position, radius, or position in the XY location. Okay, so I won't dive into that. I wanted to pause. I'm going to talk some about how we estimate the intrinsic camera parameters, but I want to pause for just a second and talk about how you could do it without the tools that we use. What's the kind of ideal case, or how would you get at these values if you didn't have any automated or computational way of estimating camera parameters? So in the ideal case, your lens distortion is 0, and maybe going back real quick, it looks like this one on the left. You have no distortion, so your lens distortion parameters are all 0, that they just kind of drop out. In the ideal case, your principal point would be at the camera center. So, and this is one that you have to kind of think about a little bit, but I think people always kind of assume, hey, that the center of the camera would be right at the center of the image. That's just not the case, but in an ideal situation, if you want to just make an assumption, you can assume that the principal point is at the camera center. And the focal lengths are calculated by knowing horizontal and vertical field of view. So if you have your horizontal field of view, you can, again, I'm going to simplify it, or sorry, in this case, I'll do vertical field of view. If I knew my vertical field of view in degrees, so I'm measuring this angle, which is how much I can see with my camera. Half of that field of view would be this angle I'm showing right here, the angle in the bottom right corner. So that's 1/2 of the vertical field of view. And then I can just use the geometry of this triangle again. This small triangle here. So my image is, call it h, the image height is h, so half of the image height would be h/2. And my focal length that I'm trying to get an estimate for is just this fy. So from that triangle, I get that fy is 1/2 h divided by the tangent of the field of view over 2. So it comes out to be a pretty simple formula if you want to convert from an angular field of view into this focal length in pixels. Again, that's the ideal. Okay, but now in practice, like I said, that's not what you see, especially, the cheaper the camera you get, the less likely it is to have really well, low distortion, everything aligned in the center, that sort of thing. So how do we measure that? We've found to be really useful is to use a calibration target pattern. Classically, this has been done with checkerboard targets, but as things have evolved, there have been lots of new target patterns that have been involved, that have evolved and come on the market. The one we've chosen to use is called a Taruko target. It's basically an interesting combination between a checkerboard, so you can kind of see the checkerboard style on here, and an Aruko pattern. And the Aruko pattern are these little boxes in each of the squares that are kind of like QR codes, right? They're binary patterns that allow you to encode a specific marker for each of these boxes, and to be able to estimate that marker, ID it very reliably. So what's nice about this is that the checkerboard gives really good corners, right? So one of the things you want to do when you're doing these estimations is you have to estimate some points in the image very reliably and very accurately. So we can estimate corners on the checkerboard pattern with a high accuracy. But we also have kind of this known target pattern where I can isolate individual parts of it and kind of really identify where I am in the image. And it's a known target pattern. So we print this and we know where everything's located, so we can get really good estimates. We can also build a coordinate system around this that usually is like the bottom left corner will be an origin for this board. And we currently buy them from a company called calib.io, but you can always print these out yourself, and they give pretty good results. Okay, so one thing I want to mention, and why having kind of the scale or knowing the pattern and the board is important is typically in projective geometry, what you lose is a scale factor. And so knowing the scale of the objects is really important. And you can kind of imagine that a little bit is if I show you a board to a camera, and I don't know anything about the board, you can't tell the difference in projective space between a small board up close and a larger board far away. They all project down to looking at the same thing. But when I know how big each of the boxes on the board are supposed to be, then I can pin down how far that board is away. So in other words, a big object far away looks the same as a scaled down object, but once I know the size of that object, I can figure out how far it actually is. And I mentioned that for two reasons. One is because that's important for the calibration piece of it, but also as I talk about localization in just a minute, the localization really relies on that idea that by knowing where things are in the world and knowing kind of their location and distance, I can pin down where the camera is relative to them. And that's how we do localization. Okay. So this is I just wanted to mention and provided some links here. OpenCV again is really handy here. It has functionality for detecting Taruko patterns, extracting the features, matching them, estimating the intrinsic calibration parameters from them, and even giving a 3D estimate of camera pose with respect to the board. So it does all this functionality. So it's really a handy toolkit for being able to do the camera calibration. So once you have this, it really makes the process relatively simple to do that. And I think I put in a link later. All this is in our GitHub repo. So if people are interested, they can check that out too. So I just want to walk you through what this looks like. So you would start with a Taruko board. This is a target pattern like this. This is just a board that's about 1 meter wide and has lots of target patterns on it. I will make one note. This is the only board I had at home, so I use this one for illustrative purposes. But typically this one has a lot of small patterns on it, which is used for high resolution cameras. When in practice, what we use is one that has what's called a coarser grid that is used for lower resolution cameras like the ones we use. So although I'm showing this fine grid one, I'd probably recommend people using a coarser grid if they ever want to do this type of intrinsic camera calibration. Okay, and then just to dive into a little bit more detail on the Ruko features. So if you start with this board and zoom in a little bit, it looks like this, and then you zoom into a single cell, it looks something like this. So in our case, we're using a 5x5 Ruko pattern. So each of those cells will have a unique pattern of kind of, again, binary dots, if you will, in a 5x5 pattern that allows you to uniquely identify each of the cells on this board. And there's a whole dictionary that is used to look this up. But it's really helpful for making sure you've got the right patterns and localizing within the board. So we use a command, again, right out of OpenCV. There's a Ruko package there that allows us to detect markers. So when we do that, run it on this image, you can see that what it's doing is calling out for each of the patterns an ID for the pattern that was detected, and also identifies the corners around those patterns. So it's actually localizing the corners. That's going to be really important for making an estimate of the camera calibration. And it is doing that across as many features as it can detect. And the key here, one of the nice things actually about these Ruko true Ruko boards, is you don't necessarily have to have the whole set of patterns detected. You get just a nice coverage. And when you're doing the camera intrinsics, what you're trying to do is kind of cover the lens with different views of this target object. So you want to make sure that you're getting sample points all around the lens, because at the end of the day, what we're going to be doing is trying to understand the distortions and the camera center based on knowing where these points are relative to each other, and understanding, kind of mapping what the camera intrinsics have done to distort where those points are relative to where they should be in the ideal world. So that's how we're going to figure out the camera intrinsics. So again, just to maybe really drive that point home, a typical localization procedure might include 30 or 40 or 50 sample images where we've taken the board and we've moved it at different angles around the camera to get good coverage, so that we're getting sample points all around the camera lens. You want to really, especially around the corners where the distortion is the most, you want to make sure you've got good samples for the algorithm to be able to do a robust estimation of the intrinsic calibration. Okay, so and here's an example of that, right? We're just trying to get move the target around. In this case, you can move the camera around just as well. Actually, that's probably what I did. Now that I think about it, was moving the camera around just to get different views relative to the board, and then we're going to compute the intrinsic pan. So we're going to extract all those features. Again, you can kind of see how we're getting coverage now around, say, like the top right portion of the board, the center of the board. Actually, these are both kind of in the center of the board, but we'd like to get also good coverage around the lower left, lower right, and so forth. And then we'll use just another function out of the OpenCV library to calibrate the camera. One of the things this does, it allows us to undistort images. I've kind of zoomed in here just to give you a sense of some of this distortion that I was talking about. And I don't know if you'll be able to see it very clearly. I'll drop a reference in line in just a second. But in theory, straight lines in the world should map to straight lines in the image. But with distortion, that doesn't happen. And so what you can see here, and I've kind of zoomed back and forth, is the original image that's distorted by the camera lens, and a corrected image where you can see we've kind of corrected and straightened out. So this is the undistorted image that we get by using the intrinsic camera calibration. And so if I look at it again, like this is the original, you can see how that straight line, which is the top edge of the board, isn't straight in the image, but when I do the correction, it becomes a straight line. And that's another kind of key point in these intrinsic calibration procedures and doing undistorting of the image is that you start to get a real representation of the world that's more accurate. So again, just to kind of go back and show that one more time, you know, this is the original image, and then when I correct it, I'm able to rectify things. And the output of this whole process is basically just a set of parameters. It comes out as a matrix of intrinsic parameters, just that historically this is how it's done, and there's actually some reason behind why you want it in this form. But it has the focal lengths that I mentioned. So in this case, 390.5 pixels in X and 390.35 in Y, and the center of the camera. So 345, roughly 234. So this is for a 640 by 480 camera image. And so you can see this is how it differs from the ideal. So if you think about a 640 pixel wide by 480 pixel image, you expect the camera center to be at 320, 240, right in the middle of the image. But instead of 320, 240, it's 345, 234. So you can see it's off by, in the X direction, the camera center is off by almost 25 pixels. So if I were to think that an object was in the center and say, hey, this is right in front of my camera, dead in the middle, I would be off by 25 pixels by, I'm not sure what that is. It's not 10%, but it's, by certainly a few percent. And same thing in Y. And then the distortion coefficients, again, I don't want to spend much time on those. Ideally, they'd all be 0. These are the distortion coefficients, and the latter ones usually are pretty small because they're slightly higher order. But anyway, the coefficients, these are the coefficients that get derived, and again, those are the ones that are used to help straighten out lines, kind of undistort images. And then this is kind of the tie into what I'll talk about next in terms of how we find where we are in the field. We can also use this to estimate pose, meaning the 3D location, position, and orientation of where the camera is with respect to the target. And like I mentioned, we kind of pick a reference frame on the target. It's usually the lower left corner of the board with the z-axis pointing out. And now we can, whenever we find this target, find enough features in the image, we can compute where the camera is relative to that board. And conversely, what I can do is draw a reference frame on the board in the image space, right? So I'm able to kind of draw this virtual reference frame that kind of allows me to verify, the camera knows where it is with respect to the board, or where the board is with respect to the camera. I'm going to think about that. So that's kind of a cool thing to do. And so what we can do with that then is start to figure out where objects are on the field. If we know where they are located with respect to some global frame, we can start to figure out where they are with respect to the robot, and where the robot is with respect to them, which I'll talk about in just a second. Another thing, just to reference, we can start to do things like stereo cameras or multi-view cameras, where if cameras have some overlapping reference point, I can start to triangulate and figure out where they are relative to each other. And also, we're going to need to do things like figure out where other parts of the robot are with respect to the camera. So that's that's going to be hopefully next year's talk. Someone from Spartan Robotics, myself or someone else, will talk about the extrinsic calibration that we're doing, but we'll leave that for the next time. So I wanted to show a real quick video of 971 robot in action. It'll start in autonomous mode, and you'll see it shooting, the one right in the center of the image, shooting the images. And I apologize if that sound is really loud. And then the second one is a distance shot from over in the lower left, where you can shoot us shooting from outside there. Again, and then just I included the climb just for complete. Okay, so that's the 971 robot from this year. We competed in a couple competitions this fall. It consists, I won't go into details, but there's a ball intake. There's a vertical column where we accelerate the ball, and a hood that lets us shoot out. That hood has a turret, and I'll point out. Actually, I'll probably point out the cameras here because I think this is a pretty good image of it. But it has a turret that can spin and face the target, so that you don't have to have the robot facing the target, and a hood angle that allows you to adjust up and down to get the right height and elevation on the ball. And what we've done is actually put 5 cameras on the system. So there's one that it's a little bit hard to see, but it's kind of mounted at the top of the turret here, that swivels with the turret. So it's always facing where you're going to be shooting, which is really nice because that allows you to hopefully always have a view of your target. And then we added 1 camera kind of in each of the, each call it orthogonal direction, forward, back, left, and right. But there's an additional camera, and you kind of see, it's a little bit hard to see, but you can see this one here, which is slightly elevated, pointing up, slightly tilted up, but is looking forward. And then there's one on the left, right. I'm not sure you can really see it. The one on the left here, there's one on the back and the right. So it gives us coverage. So no matter which way the robot is facing, ideally there's some camera that's seeing the target, as well as the turret camera. So that's kind of how we set the system up. And again, the idea is that we wanted to be able to always be estimating our position, and allow the robot to track the target using the turret camera. So again, I've kind of gone through this. There are 5 cameras, 1 on the turret and 4 on the body. Okay, so let's talk about what we're trying to do. So again, I'm going to shift gears now into this visual position estimation. So how do we visually estimate pose? I wanted to just start with some kind of the design principles. This is a pretty rough list, but some of the guiding principles that we wanted to be able to do. First was using off-the-shelf cameras and processing. We didn't want anything super fancy or complicated or expensive. So we're using a Raspberry Pi. We're using off-the-shelf cameras, the large cam camera with a lens that is pretty low distortion, but it's just a very small M12 lens, 90-degree field of view. We wanted to move from, or we want to make sure we didn't have any requirements for special lighting, and our goal there was also to get rid of any projection of lighting that we had to do. So we just wanted to use ambient lighting, the existing lighting that came with the field. We also wanted to try and get rid of any constraints on the visual targets. We didn't want to have to use the reflective tape. We were trying to move past that and not require any markers on the field. I will say the one catch here is that we are doing a visual feature extraction, and so we need targets on the field that have some visual richness. They need contrast or gradient or edges or corners in order for us to be able to detect them. So you couldn't have a plain white background and expect this to work. There needs to be some visually rich information on the field that we can use. We also wanted to be able to easily retrain the model. Came to competition day, and we had to, for whatever reason, retrain the model. That needed to be quick and easy to do. And I'll talk a little bit about how we converged on basically just taking a single image to be able to retrain the model. We wanted to return the full pose of the robot, so the position and orientation in 3D, and where it sat on the field. That wasn't a requirement, but we figured we would try for that. And we've had some discussions. We had some great discussions with a team from Israel at the Chessy Champs competition about they had done a similar thing to us, but estimated just constrained to 2D pose. And I think there are pros and cons there, but for us, we decided to just go with the full 3D pose. And our desire was to run at about 5 to 10 hertz. So we started shooting for 10 hertz. We ended up closer to 5 hertz, but being able to run the vision processing system 5 to 10 times a second. Okay. So this is this is kind of an outline of what I'm going to talk about, and I'll go into the detail on each one of these. But here's kind of the workflow of building this up. So the first thing is to build a model. And I'll talk about each of these points in detail. The second is then compute the camera pose on the field. So where is this camera with respect to the field? Then we need to fuse that into an estimate of the robot pose. And this goes back to, I was talking about, so the computing the camera pose on the field, let me mention, relies on the intrinsic calibration being good. And then estimating the robot pose relies on the extrinsic calibration, knowing where the camera is with respect to the robot to be able to estimate that pose. And we're using the extended Kalman filter for that. And I won't go into the details on that one because it's pretty involved. But just to say we're fusing that with motion data from the robot to get an estimate of where the robot is in the pose. And kind of as an aside, we're doing that for all 5 cameras. So we are running this pose computation locally on the Raspberry Pis, and then sharing that information centrally, and it gets fused into a single estimate of the robot pose. We do bias towards the turret camera because that's the one that's most likely seeing the target and having an estimate of the target location relative to the turret also. So it's good for directing the how we're aiming during the shoot. Okay, so let me jump into this, and I apologize if I think I've got enough time, so we'll keep kind of cranking through this. So building a model, let me start with that. So we want to build a model. The way we're doing it, we're doing this visually. We're basically saying, just at the top level, what we're saying is I am going to have a model of what I think the world should look like. I'm going to then later come in and take a picture of where the robot is and what it's seeing in the world. I'm going to compare those 2 images and then figure out where the robot is with respect to that first image. Okay, so the first thing we have to do then is capture a reference image. So this is the image that I'll refer to as our model. And the model actually will have some additional information on it, but this is kind of our template or model image. And we just do this by using one of our cameras. So we just capture this image. Okay, so if you see this one, and one thing I'll highlight is you can see this. I don't know if you can see it, but it says field reset here on the displays. So that's the reference image. And then with that reference image, what we want to do is identify known points on the image, so where we know their 3D location, and associate that with points in the image. So we have kind of a manual process here where you capture the image and go through a sequence of identifying points on the image where we know that 3D point. In this case, we've chosen, for example, the kind of outline of this target pattern, because this is going to be our model. And so the first thing we'll do is, and we have a UI that we built to do this. First thing we'll do is it'll guide you and say, okay, select this target point. So you go into the image and you select the point that is the lower left corner of the target, the power port, and we associate that with a 3D point in space, because we know on the field where that point is. It's 8 meters from the center of the field to the back wall. It's I don't remember what it is, but let's say it's about a meter and a half from the center line to the target, and the vertical point is 0 meters off because it's on the ground. So it's 0 meters off the ground. So we associate that image point with a 3D location in space. And we're going to go through and do that for several points in the image. So pick kind of, this is a little bit like the armpit of the target. And we go through and do this for out on the wing, and continue this process. So in this case, we've picked about 7 points that are kind of our reference points where we know the 3D location in space of each of those points. And we now know the 2D location in the image of each of those points, and we can associate them. And one of the things, and I won't have time to really dive into this, that we can do then is build a map, and this is called a homography. And homography is a map between two planar surfaces. So what we can build out of this is a homography that maps points in the image plane. So the image plane is a 2D surface. So points in the image plane, which are the, kind of my yellow circles, to a 3D plane in space, which are the locations in 3 dimensions of the target points. And so I want to just make sure to stick with that for just a second, because it's a little bit tricky, and in retrospect, I wish I had a little bit more detail on that. But the idea is now I can map any point in the image to any point in space that is on that plane, which is the front face of that target. And this is kind of an interesting piece to note in that I'm not saying I can map any point in the image plane to any point in space. It's just a planar surface in space, and it is the front face of that target. So anything that's in that plane, if I asked you a point, let's say just some random point in here, which is where this logo is, and I gave you that image coordinate, the homography would tell me where in space that is in 3-dimensional space, kind of X, Y, and Z. That point is located on the planar surface of this power port. So it's just planar to plane to plane, but we're going to use that as we go forward. So that's called a homography, is that mapping between 2D points and 3D points, between two planes. Okay, so then what we're going to do is extract a bunch of feature points on this target that we're going to use to later recognize where we are in space. There's lots of ways to do this. We're using SIFT, but you could use orb, surf. There's a bunch of feature extractors that essentially go out and try and capture relevant, significant highlights in the image. And it's very often I tell people, think about like corners and edges and gradients, but places that are visually interesting. And so each of these circles represents a feature that was extracted from this image, and that we will then later be able to recognize and detect in a subsequent image. And then the key here is now we've got our image model, which is that model, the image we captured. We've got a bunch of features that in the image plane that we've extracted. And with this homography, we can then map those to 3D points in the real world that are all 3D points in this plane. And one thing I'll call out is there's a few points here that are not in the plane because this wing has a fold. And so we actually reject those. We get rid of those. I haven't shown that here, but we only do it on points that are on this planar surface. That makes sense. And we could have used potentially some that are off this target, but we restricted our attention just to that little polygon that I drew earlier. Actually, I'll go back to it. So this polygon, we only look at features that are within this space because we know they're planar in the real world. And so we use those. Okay, so now we have what I'm calling the model. We have key points or features that we can use to match for later, and we know where those features are in 3D space. Okay, so during the match now, so now we've got our model, and we want to shift to how do I localize on the field, and how do I figure out where the camera is on the field. So during the match, we're going to just take a random image, and so this is again just a different image, and you can see right, how the display has changed a little bit here. And let's see, I'll flip back to it, but you can see the perspective is different. It's just in a different location, and a little bit further away, shifted slightly in its pose. And during the match, we're just continually capturing those images. So capturing images around 10 hertz, and trying to process them to figure out where we are in the world. And so we go through and we again extract features. So we'll take this image and extract the features in the same way we did with the previous one. And then we're going to match them up. So we, again, using these feature matching tools. So as I mentioned, we're using SIFT, but you can use other tools just as well. We're taking our model image, which is the one on the right here, and matching the features to ones that have been detected on the left. Okay, and each of these lines going across these two images is a correspondence. Is a feature that was originally detected in our model image and now has come back and been detected in our new real-time image, the one we're trying to compute the pose of. And so that shows you how it's computing and matching up these features so that we're going to be able to figure out where things are. And I'll just mention real quickly, these boxes are basically transforming where the robot thinks this image, the outline of this image, would project to in this space. And you can see it's not perfect, but the idea is that it gives you kind of a rough sense of where things are. And this circle here we just drew on for reference is kind of a projected point from the center of the target, just to see that we're tracking properly. So this is just a visualization tool that we wrote to help with this. But now, let me emphasize, what we have here is a set of features that we have extracted from our current image and reference back to the model. And we can tie each of those feature points to a 3D point in space also, because and by assuming that it's in the same place as the model was. So, you know, we maybe just to give an example, we detected this point. Let me find a good one that's easy to reference. Maybe start at the top left. So we detected this point up here in the top left. We said, okay, that point in space, based on all the things we did to begin with, our homography is 8 meters from the center of the field, you know, a meter into the field, and whatever it is, 2.5, 3 meters high in the Z direction. And that was where it was in the model. And it matches this feature over here. So we say that this feature in the image must be in that same location. And we're going to use that then to extract out where the robot is from all of that. Okay, and we do that by building up this map. So it's all the features from our current image. We now know their approximate 3D location based on that reference model. And we're going to use that to compute the pose. And fortunately, again, OpenCV to the rescue, there's a routine called solve PNP that does just that. So it takes 2D and 3D correspondences. So it takes image points in 2D, it takes the camera calibration information and the 3D locations associated with that image point, and it computes where the camera must be relative in the world to give that projective correspondence. And so what you see there is we are now able to say, okay, the robot must be approximately here on the field. This is kind of meant to be an overhead shot of the field. The robot is the red, and the target is its view on the target shown by this blue line. But so this is the pose that gets estimated by using those 2D and 3D correspondence. Technically, you only need 4 points to do this estimation, but we require at least 10, and that allows us to solve for the 3D pose of the robot. And I'm just showing a planar projection where it is in kind of the field, like an overhead view of the field, but it really is a full 3D estimate of the robot. Okay, and that, again, is just a really nice routine that allows us to do that. Just some notes on that. One of the reasons I tie this in with intrinsic calibration is it's really important for getting a good estimate of the pose of the robot. Again, it goes back to this thing that I was trying to emphasize. If my camera center is off by a little bit, then when I try and do this correspondence between 2D and 3D, the whole estimate of where the robot is going to be off by a little bit. And we saw that significantly. If we just use a default camera calibration that I highlighted, where kind of the ideal case, then the pose estimate wasn't any good. It was significantly off. But as soon as we calibrated the camera, then the pose is really good. There's a bunch of different ways you can use solve PNP. We started with Ransack and tried that, and Ransack, I'm not going to go into the details, but is kind of a iterative random sampling and consensus algorithm that is usually very robust to outliers. So it's good at rejecting noisy samples. So we thought that would be great. But we also, what we found was that the estimates that came out of RANSAC tended to jump around a fair bit. So we moved to just an iterative solver, which we found provided pretty stable estimates. We also found that it's really important to provide the previous estimate as a seed that helps kind of guide the solver to the right place. And so that was just something to note. And the estimate you get is a little bit jittery. I don't want to say it's perfect. You know, it's pretty amazing that I think that we can even estimate location based this way. But it gives really accurate heading relative to the target. So if you're just trying to align to a target, it's really good. And the distance to the target was also quite good. And you know, this is just a ballpark estimate. We don't have absolute values on this, but I'd say that the estimates had a variance of around 10 centimeters. So if you're trying to localize on a 15, 20 meter field, you're able to localize down to about 10 centimeters. So pretty solid estimates. Okay, so now we've got an estimate of where the camera thinks it is on the field. And now we need to estimate the robot position on the field. And so, so the first thing to mention, again, I talked about camera calibration. This is where the extrinsic camera calibration comes into play. I need to know where the camera is relative to some robot frame, especially when we've got 5 cameras. Each of those needs to get mapped into the same reference frame, and we've chosen the IMU location as our reference frame. So the IMU kind of centers the robot, and we map all the poses down to that reference frame. Again, we've just used CAD values in this. We're doing some work on how you can figure out and estimate your extrinsic calibration by using Chiricahua targets and an IMU to kind of figure out how they move jointly. So that's going to be really exciting work. And then one other thing we do some basic filtering to just make sure the pose estimates are same. One thing that happens is we have targets on each side of the field that look very similar. So we basically made sure that if the robot estimate, the camera estimate tells the robot that it's pointing 180 degrees in the wrong direction, we just reject that and get rid of it. There are some issues I won't deny about if your pose estimate is completely off, we won't easily recover from that, but there are things we can do to get around that. And also we want to make sure that for example, the estimate is within the field. These estimation procedures can sometimes have unstable points that they map to, where the robot, say the target is actually virtually behind the robot, or it sends it significantly off the field. So we just reject those. So there's an outlier rejection that we do there. But then the key there is we want to fuse that in. So we fuse that camera pose estimate after translating it into the robot frame, the IMU frame, using an extended Kalman filter. And we play a little trick with that by converting the heading and distance from the camera estimate into an observation based on the current robot pose. So we rely a bit on the current robot pose, but it allows us to converge everything and kind of more heavily weight the heading and distance from that we get out of the camera. Okay, and we do that for all 5 cameras, the 4 kind of ordinal directions and the turret. And that's basically where we got. And I'll mention, you know, pose estimates we computed at about 5 hertz with a variance, like I said, around 10 centimeters. I don't have we didn't have like a global positioning measurement system to compare that, so I don't know in absolute dimensions. But what we found was that the field, we were able to localize the robot generally pretty reliably on the field. And in particular, we're always able to aim really well towards the goal and have a good sense of distance for kind of, especially when you think about shooting, to get the right elevation and the right speed of the ball that we're shooting. So we were very happy with how that worked out. And it was interesting, during the competition, there were a lot of comments about how we were able to always know where the target was, and had just, our aiming was always pretty solid. A couple call outs, we saw some fairly significant blur when moving, especially rotation, and our turret could rotate. I don't remember what the value was, but it was really fast, right? So it can spin pretty fast. So there's significant motion blur that you just have to deal with. In particular, we would do really well when we could stop and shoot at the target. And given that we're shooting 5 balls, we could be correcting doing that. Fusing with the IMU readings also allowed us to maintain aim while moving. So you can imagine that the robot's moving along or even rotating, and the turret is able to track because it's got IMU readings also that are helping it out there. So and this is typical in robotics, where you want to kind of fuse the information, the kind of fast but only relative or local measurements from an IMU with kind of the more slower global positioning that you get from, in this case, a camera, or you might get from GPS, something like that. So this is a pretty typical type of fusion. Another call out is just that we're pretty happy with. It's not required, but we could just use a single image for our model. So it kept things pretty simple in terms of training the model. We just captured one image that was our reference image, and that worked. And the nice part was that worked throughout the entire competition. So we took the first day, in practice of the competition, and we were able to use that same image regardless of the time of day or lighting or anything going on throughout the whole competition. And that's partly because these SIF features are pretty robust, but I'm sure that could be expanded and improved on. But for us, it was a nice advantage. And then maybe just a couple call outs and I'll finish. Ideas for improvement. There are other types of features. We're looking at one type that's a neural network inspired key points called NIFT. As I mentioned a couple times, we're automating the extrinsic camera calibration. We're working on some other camera improvements to reduce sensitivity to motion blur. We'd like to understand the effect of having more targets in our models. For this competition, we focused just on the power port, but you could have targets all over the field and be able to localize wherever you want. Also, we may potentially need to, we didn't do it this year, but do color disambiguation so that you have 2 power ports, a red and a blue one, and at this stage, we had some ability to disambiguate between them, but you could use color. We weren't using color, but you could use color to tell the difference. Okay, I know I'm out of time, so I will stop there and take any questions or have any discussion.
Thank you, Jim, and what an excellent presentation and interesting topic, and what a complete slide presentation. Just a quick reminder for all of you: all the presentations are recorded and will be, well, eventually posted and released, so you can check part by part and, well, specify anything you may want to. So before we move on, though, we indeed have some questions for you. So the first one from an anonymous attendee says, do you recommend this method for a team without a practice field?
Yeah, it's a great question. So we don't have a practice field. I think my answer is a tentative yes. It really is a great question. I wish I had a picture that I could pull up easily of how we set this up, but we built a practice target, right? So we had a power port built out of plywood. What we did was added features to it. So we did that in a couple ways. When we first started, we just put some duct tape up and just made little strips of tape that would add some texture to it. And then later on, we printed out a couple of the sections just on paper of what the target should look like. But the key there was we could use that as our model and train it, and all you needed was that. You didn't need a whole field, you didn't need anything else, but you could localize just using that. So I think it was pretty successful, us being able to develop this without a practice field. There are some challenges in terms of each time you go to a different field, you have to then go through this calibration or this model capture procedure, as opposed to just having using the reflective tape and doing it that way. But it turned out that worked pretty well for us. So I think I recommend it. I think I mentioned, there are a couple teams I know that were doing similar things that I believe were just using the reflective tape that's available. And that's certainly an option. That might be the place to start. I think you can still do a lot of the same ideas, but using that reflective tape as your kind of features that were in space. But anyway, maybe hopefully that answered the question. I think it's very possible. Like I said, we did not have a practice field. We just had a fake power port that we use.
Yeah, I think it does answer it. And well, moving on to the next one. Another anonymous attendee asks, could those libraries be used in Java?
Oh, interesting. I don't know. We have code that we've used both in C++ and Python. So the answer for sure is C++ and Python. I honestly have never, I'm pretty sure OpenCV exists for Java, but I've never used it. And so I can't really answer that question.
Yeah, no worries.
You've got OpenCV. OpenCV is really all you need there, right? So if that works for Java, then yes.
Yeah, even if some of the attendees here could help in the answer, well, the chat is always open. Also, our programming mentors, some of our programming mentors should be here in the webinar, so they could help as well. Great. And another question, could you talk about a little about your 2019 vision system?
Not a lot, because I wasn't involved in 2019. So I started in 2020, just in time for the pandemic. What I do know about the 2019 vision system is that it used kind of a more traditional method, which was projected light, so a flash of light with the reflective targets, and extracted the location of the reflective tape, and did localization there relative to the target. I know one of the big complaints was that you couldn't tell which target you were looking at. There were similar looking targets, and they had a really hard time with knowing which target was which, especially in autonomous mode. And so that was one of the motivators to move away from that and get something that could more uniquely identify the targets and be a little bit more robust to that.
Okay.
But yeah, unfortunately, I wasn't there on the team. So.
Yeah. You entered in 2020, right, with the pandemic?
I did, yeah.
Okay, no problem. And I think our last question, what do you think, or what are your thoughts, if you have, on the Limelight?
Mm-hmm. Yeah. Again, I've never worked with the Limelight, so I don't have a ton of thoughts on that. I think it's a perfectly good system. I think the thing that I like about where we've gone with this is that we get to control the camera. I think it gives us the ability to choose exactly what we want in terms of field of view, in terms of the processing that we're going to do, and it doesn't require kind of that pulse of light. And so we've been really happy with it, and it doesn't require reflective targets, right? And so I think that's where we're pushing it, is to say, hey, you don't actually need this. You can do it all with just pure vision, and try and move towards that state. We also, though, have proposed, having said that, I would love to see FRC or somebody, FRC, put some visual markers on the field that were purely visual, didn't require the reflective tape, to challenge teams to look at how can we process visual information and kind of enable that. I think it'd be really nice to have some types of, again, characteristic markers, maybe something like these Aruco patterns, that allow you to do localization, again, purely visual without having to rely on reflection.
Okay, and well, another question, going back to the 5 cameras model you showed us of your robot, just as a confirmation, someone asks, all the processing for the 5 cameras is made in one Raspberry Pi,
no,
right?
No, each camera had its own Pi. So yeah, it's a great question. No, we that we wouldn't be able to do all of it on one Pi at that frame rate. So I think we could probably do 5 cameras at basically 1 hertz. If we want to do it all in one Pi. And the catch there is that is the Pis right now use a MIPI cable, MIPI interface to get it onto the Raspberry Pi from the camera. And there's, I believe, only 1 set of lines for that. So you'd be limited on how you brought the information from the camera to the Pi, although potentially you could do USB cameras or something else like that. So, but yeah, currently it is 1 Pi per camera.
Okay, well, I think we're done with questions. So again, Jim Otworski from Team 971, thank you very much for being with us. Just any contact information we could have for the team or for you, so they can reach out directly.
Yeah. I'll share my email. I mean, it's yimmy13@gmail.com. But yeah, feel free. You guys have my contact information. You can share that out. I'll share the slides with you all also, so if people want to be able to look at them in detail, especially because there's some links in there, I'm happy to share those. Yeah, and feel free to reach out with questions. I'm happy to talk about it.
Yeah, we appreciate that. We have a lot of teams from almost 9 different countries connected and registered to the warm-up. So I think they'll be more than pleased to maybe get in touch with you for any more specific doubts. Yeah. And well, Jim, again, what a pleasure to have you with us. We know you got a lot of things to do over there in Mountain View with all the folks at 971, the winner team for the Galileo division in the last Houston champs in 2019. So it's been great to have you, and we hope to have you soon, or any other member from 971 in future events.
Yeah, thanks very much, and good luck with your season coming up.
Yeah, the best of luck for all of you there. Thank you very much.
All right, have a great one.